Hello, everyone. I'm Utkarsh. I'm from Google Munich. I've been working on Clang and Clang frontend and Clang tooling. Today, I'll be talking about C++20 coroutines. What are they, and what are the common lifetime issues that we can encounter while using coroutines, and some ways Clang developed in Clang how to mitigate and detect those at compile time. Let's start with what are coroutines. Coroutines are basically suspendable functions which can suspend themselves, and other entities can resume them. On suspending, they store their state in, in a global state, and they on resuming, they can restore using the same state and continue execution from the point where they suspended themselves. So they can suspend themselves using the co-await keyword. Let's try to see what lifetime issues we can encounter while using them. Before that, let's dive into the control flow, what control flow happens when you are using a coroutine from a simple function. Let's consider this user function below. It constructs a path local variable, and it passes it to the read coroutine, and the read coroutine then the execution of the coroutine starts. The read coroutine accepts the stitch string reference and stores it in its state, and it executes until its first suspension point is reached. The first suspension point is the co-await get handler, and at this point the coroutine suspends itself and returns the control back to the user. And once the control reaches back to the user, the coroutine itself has not completed, and it will be resumed at some other point of time in the future. But the user now has the control, and a lot of things can happen to this path variable, the reference to which was captured by this coroutine, which is not yet completed. This could essentially become dangling at some point of time if the user destroys it at some point. And this is not very hard to get wrong. This is very easy to make the coroutine capture dangling references. For example, if you consider a get file name function, which returns a stitch string, and if you use that as a parameter to the reference, as an argument to the reference parameter, the coroutine would be capturing a reference to this temporary. After the coroutine suspends itself and the user starts executing, the temporary would die after the full expression, but the coroutine itself has not completed itself. And once the coroutine is resumed, the rest half of the coroutine function would be use after free, and this would get you use after free. Same things could happen when you are passing a local variable to this coroutine, and the user of the function just stops itself by returning the result of the coroutine, and the local variable that is sent dies, but the coroutine is not completed yet. This is again use after free. Let's try to see some ways of detecting these lifetime issues we developed in Clang. Let's try to see what is the formal condition that we want to check, and just establish some understanding of what's going on. So consider this add coroutine, which accepts a reference and returns a task object. One of my understanding is you can model this as this task object contains all the data that is required to resume this coroutine, and this somewhere down the line contains a coroutine frame, which again down the line contains this reference, that is the reference parameter that was captured by this coroutine. And in order to things to work correctly, the lifetime of the argument that is going to be passed to this parameter should live at least as long as the return object is alive. You could say that the return object is the coroutine, has the same lifetime as the coroutine. And this itself is not a new problem to C++. You could consider something without coroutines, in which you could have a function that accepts a reference and returns a result that captures the same reference. And in the bar function below, if you pass it a temporary 0 to this foo function, the result R would capture this reference to this temporary. After the first statement, the temporary 0 would die, and the second statement R.X would be a use after free. And Clang already tries to resolve this or identify this at compile time using Clang lifetime bound annotation. So there is a lifetime bound analysis in which you can annotate a particular parameter of a function as lifetime bound. And Clang enforces that whatever argument is parsed to this particular parameter, this should live at least as long as the result, the return object. And it works on initialization expressions. So the object that is being initialized should have a lifetime lesser than the lifetime of the argument that is being passed to this particular function. For example, in this, Clang identifies this as we are using address of a temporary to initialize a local variable R, which would live beyond, and the temporary itself would die after the full expression. And we basically extend this lifetime bound analysis to coroutines in order to say that any reference parameter of a coroutine should be implicitly lifetime bound without actually wanting to write lifetime bound to every parameter. So we introduce coro lifetime bound annotation, in which you can attach this annotation to a coroutine return type, and Clang would consider every function that returns this type as implicitly lifetime bound to all of its reference parameters. In this way, you could see that you will be able to identify all the issues that we discussed in the beginning. For example, if you are using plain return, you are passing a reference to a local variable int n to this particular coroutine. And the n here, n in the user, is a local variable which dies after the return statement, while the coroutine return object does not. And Clang would be able to identify that you are basically returning an address to a local stack variable. And similarly for temporaries, if you are going to use a temporary to call a coroutine and store it somewhere, Clang would be able to identify that you are using create request temporary here, which would die after the first statement, while the task that is being initialized here lives longer than the first statement. It lives in the local scope of the user object. And it identifies that, task lives longer than the argument which was lifetime bound. And this way we basically identify all the issues. Some of the places in which this does not work is one of the limitations of this approach is it only works for a single expression in which an entity is being initialized. So, for example, if you introduce control flow here, for example, you use a local request in the user function, you use a local scope variable R and construct and call the coroutine. You construct this task, so Clang would not be able to reason about or compare the lifetimes of the task and the R variable, and it would not be able to detect it. And this is something it lacks, and it would benefit both lifetime bound analysis and coroutine safety. So in the end, this is I just wanted to highlight how easy it is to get C++20 coroutines wrong, and there are some mitigations in place in Clang which can help in coroutine safety better and just make the life a little simpler. Yep, that's it from me.